Hi, I'm Professor Ladelia Jordan. Today, we're going to be working with K nearest neighbors. So let me share my screen so we can get started. Again, today we're working with K nearest neighbors or kNN. I'm going to explain the idea, show practical choices you control, then we'll run a short SAS Studio demo so you can see what the output looks like. By the end, you should be able to answer three questions without guessing. One, what kNN is doing when it makes a prediction. Two, why scaling can change the result. And three, where to look in SAS output to judge how a model performed. Let's start with the idea. Okay, kNN is one of the most intuitive supervised learning methods. The model predicts a new row by finding the K most similar rows in a training data set. So if the outcome is a category like a class label, we'll use a vote. The neighbors vote for the class. If the outcome is numeric, we use an average. The neighbors' values get averaged. Sometimes we give closer neighbors more influence. You'll hear this described as distance weighting. The idea is simple. A neighbor right next to the point should count more than one that is further away. One more important point before we go on. kNN does not produce a set of coefficients you interpret like regression. The training data is the reference library. Prediction happens by searching that library. If you're looking at our visually, think of points on a plot. A new point arrives, we look around it, and we let the nearby points decide how we're going to classify that point. Now I want you to picture what kNN does step by step, because this is exactly what your software is doing. So first, we choose K and we decide how to measure the distance. Next, for step two, we scale the features so one variable doesn't overpower the distance calculation. And in step three, for a new row, we compute its distance to the training rows. Step four, we predict using those neighbors by voting or averaging. If we use distance weights, closer neighbors count more. N- Now look at this note about K. K is not a minor detail. It changes how local the model is. With a small k, the model can react to more noise. One unusual point can swing a prediction. With a larger k, which you'll see in the second photo to the right, the model smooths things out, but it can blur boundaries between different groups in your data. So K is like a tuning knob that controls how sensitive your model is versus smoothing. So here on this slide is where kNN often succeeds or fails, and it comes down to distance and scaling. Distance is like the engine. If distance reflects real similarity, kNN can work well. If distance is distorted, the neighbor choices get distorted. So here are the distance types you'll commonly hear. Euclidean distance is the default for numeric features. Manhattan distance can behave differently when one feature has a big deviation. Cosine distance is when your predictors are high dimensional vectors like text features or embeddings. Now, the key practical issue, scaling. If one feature spans a much bigger numeric range than another, it can dominate the distance calculation. Let's use the tiny example on the right you see with age. age changes by 1 year, and income changes by $20,000. If we compute the distance on the original units, income tends to drive the nearest neighbor choice, even if age matters. So we have to standardize. Standardizing puts variables into a comparable scale. It's like comparing apples to apples instead of apples to oranges. Um, it puts everything into a comparable scale so distance is not controlled by one big feature. In SAS, a common way to do this is using the procedure called standardize, which is STDIZE, with the method equal to STD. It standardizes variables so the distance calculation behaves more reasonably. Now let's talk about choosing K, because this is a decision that students always ask about and have trouble with. A small K is flexible and can chase noise. A large K is smoother and can blur boundaries between classes. So how do we pick it in practice? We validate. We try a small set of K values, then compare the results on the output data. If we have like a binary classification problem, using an odd K reduces the chance of ties in the vote. A few habits to keep you out of trouble. Try a small grid of K values rather than just one value. Use the same pre-processing to train and test the data. Don't worry, I'll do a demo at the end and you'll see. If you standardize the training predictors, apply the same approach to the test predictors. So if you standardize your training, you need to standardize your test data. Keep a holdout set for a final score check, which means you need training and you need testing. Watch your class imbalance. If one class is much more common, majority voting can drift towards that class. When you compare K values, you compare performance on the test set, and you also look at the pattern of mistakes. Now let's connect the concept to SAS Studio. There's two common paths here, and the right one depends on how your setup, your SAS is set up. We're using SAS Studio, so we're going to be using the proc discrim, DISCRIM that you see on the right here. And we're going to be using with a non-parametric method. It's a practical approach in SAS, and it produces a classification table that we're going to interpret. Um, on the right, Optum A is when if you have access to SAS, the procedure fast kNN, you use that when CAS is available and you want a fast neighbor search. The advantage is you can request nearest neighbors and, if needed, distances. But again, we're going to be demoing the discrim, which is what you see on the right. No matter which tool you use, the output to focus on is the same idea. How many predictions were right, how many were wrong, and which classes were confused. Okay, so now let's look at everything with a mini example, and I'm going to go into this code in the demo, but this is the code that we're going to be running in our demo, and we're going to follow this workflow. We're going to split our data into a testing data set and a training data set, and then into a testing data set. And then we're going to standardize our variables. And the we standardize because distance is sensitive to the scale. If you look at the tip on this slide, it's very important. Um, When you standardize, you want the test data on the same scale as your training. In practice, you learn the standardization from training, then apply those parameters to the test. Otherwise, you're measuring distance in a different coordinate system. So the next step we're going to do is we're going to fit and score. That means we run the neighbor style classifier. The K value controls how many neighbors to vote. In this code that you see on the screen here, K is set to 7. I think the example that I ran, K is set to 1, but I may set it to 7 so that you guys can see the output. Um, in real work, we swap K and compare results across values. So where it says K equals 7, we run different values there so we can actually see how it affects our results. And fourth, we're going to evaluate. After the procedure runs, you're going to look for two things: the error count, or the overall error summary, and the classification table. The classification table is actual versus predicted. Numbers on the diagonal represent correct predictions. Numbers off the diagonal, those represent mistakes. And in a mistake, when you see the SAS results, I'm going to point to where those appear, and we'll translate the table in plain English. So let's look at the results. So I'm going to stop sharing for a second, and then I am going to pull up my SAS so you guys can see it. And I'm going to run my code so you can see it. So I'm going to share my screen once again. So here on the screen, you see the same code you saw in my presentation. Um, Here, when I ran this on K equals 7, and let me validate that that's what I want to do. Let's see. So yes. Um, Let me try this with K equals 1 first. And I don't see that you guys see my screen. Okay, you do see my screen. So I ran mine with a, if you're looking at my code, I set my K equal to 7, and I am going to run that. And when I run it, you can see my results here. So if you're looking at my code, when I ran the survey select here, I ran this on the iris dataset, and I set my sample rate to zero point 0.7. This means that 70% of my data is actually going to be used to train the data. And then this seed here of 7, what this does is it means that if I run this again, it will actually produce the same results. Let's see. So, this data here, it's actually this um, here. I'm going to create two data sets from this survey select. I'm going to have the train data set and I'm going to have the test data set. The idea is we need a test set so we can compare the different K values on data the model hasn't seen. Our next step in our data flow is going to standardize the data. And here we use this procedure called standardize, STDIZE. And here, this is the step that most people skip, and it matters a lot for kNN. kNN is driven by distance, and distance is calculated using differences from feature values. If one feature has a much larger numeric range than another, ex- excuse me, it can dominate the distance calculation, and the nearest neighbors might be nearest mainly because of one variable. Again, we standardize because we want to compare apples to apples. And you noticed we're going to standardize our training data set, but we're also going to run the standardize again to standardize our test data set. And these are the variables here. It's a list of variables in our data set that we are going to standardize. And notice that I am doing the same thing on the training data set that I do on the test data set. And we do that because, again, we want to compare apples to apples and make sure that everything that we're doing on our training, we're doing on our test data. So the next thing we're going to do is we're going to fit and score and with our classifier. We're going to fit a nearest neighbor classifier in SAS using the Discrim, DISCRIM procedure. And we're going to use the method, where were we? Here. Method in par. And it's very important that we use that. Now, K, this is the value that we're going to play with to try to figure out how we can get better classifications. Um, so, examples with K equal to 1, the single closest training row determines the prediction. It's very sensitive. One unusual training point can flip the result. And then we can try it with k equals 2, k equals 3, or other values. And here you're voting amongst the neighbors, which usually makes predictions more stable. We also notice we aren't estimating coefficients like regression. The model is essentially training the training set plus the distance rule. So the test out option saves predictions so we can build the confusion table. Let's see. Let's look at our output that we have. So our results are going to be here. This is our input set. This is our survey select procedure that we ran, and we ran it on the data set called ours. We set our random seed to 7, and the reason we did that is so that if we need to run it again, we get the same results. And our sampling rate was zero point 0.7 or 70%, which means that 70% of our data will be our training data. And after that, we have our discrim setup was what's we have here in this section here. and our procedure description. And you'll see in the SAS report how many observations were read um, and used, and you'll see the class information here. So there's 4 different variables initially and 3 different classes. Um, let's see. Here you see SAS is showing the class labels where we have for our iris table, the classes are Setosa and Versicolor and Virginica. And the prior probabilities here are equal. So each class is created evenly. Equal prior means SAS isn't giving one class an advantage just because it might be more common. And if you come down, if you look at the first classification summary, the one for the training data, which is here, this is the classification summary we have. This basically shows how well does the model label the rows it already stored. The big table you see at the top is what you call the confusion table. Read it like this. Rows are the true class and columns are the predicted class. So this is the class it is, and the columns is what the prediction is. On training, everything is on the diagonal, which means that the model classified the training rows perfectly. And I want to validate. Okay, so let's see. Perfect training performance is common for nearest neighbor methods since training set contains examples, the model can match very closely. This is exactly why we do a separate test set. So it also created an error count estimation for the species. But we'll get to that a little bit later, but that's very important. But before we get to that, we're going to look at the test data and the confusion table, the classification summary for the test data. Again, we're going to focus on the confusion table. Setosa looks perfect here. This is what it is, and this is what it was classified as. The mistakes are between versicolor and Virginica. Let's see. No, if I do 7, it looks like this is like 100% correct. Let's go back and change this a little bit. If we change our code and run this with k equals 1, let's see if we can get some more fun results for you. Okay, this is a little bit better for us. So let's take a step back. The training data, everything was correct on the training. So we have this is what it is, and this is what it was predicted. Well, here, if we have our k equals 1, notice that Setosa, it is 100% correct. Everything that is Setosa was Setosa, but for versicolor, 13 of them were versicolor and 2 of them were virginica, classified as virginica. And for virginica, everything was correct. Um, and you'll see that SAS gave us a 0.0444% error rate, which means that 4.4% of the test rows were misclassified, which with 45 test rows, you'll see that there are only 2 here that were misclassified. So Here, the versicolor, these are all correct because we have versicolor here. This is our actual value, and this is what it was classified as. So 13 of those were actually classified. But for the actual versicolor, 2 of those from our model were classified as Virginica. And these are the misclassifications, and this is the error rate for this model. If I were to go through and I were to run it with k equals 2, and I were to run that and look at my results, and I'm just going to go down and look at the test table and see what changes. So here, if I run it with k equals 2 for my data, you notice that we actually have an other column here where 1 goes here, and some things were not classified. So play with your k equals n value and see how this changes and see how your error rates change and figure out which one is best and which model is doing well. Going back to the k equals 1 model here, I just changed this value back to 1 and I'm going to rerun it. We just can't run 1. And I rerun my model. Let's go back to looking at this. This model is doing very well overall, but the small number of errors are concentrated where the classes overlap. Now, imagine we rent like we did, we rerunning this with the different K. What we compare the test error rate. So here, you want to compare this error rate and across your different K values to see which model, which K values are giving you better results. You're going to compare the pattern of mistakes in the confusion table and not just the total number. If increasing K reduces the test error, which means if you increase K and this number goes down, that's a sign the vote among more neighbors is stabilizing your decisions. And if the test error increases, the vote may be pulling in predictions towards the wrong class or overlapping regions. So here, when I increased my K, my error rate went up, which isn't a good thing. So you want this error rate to be lower. So if you were to write this up, you don't need to describe every single table. Focus on what K was used, what the training versus the test results look like, what the confusion table says. The confusion table, that's this classification summary you see here. Um, what does that look like? What is it saying? Which classes are getting mixed up? And your test error rate you're using to compare the models. Let's see. So here, another thing that was created is my actual output data. And for this output data, this was done when we ran the split. And there's a couple of things that you see here. What this does is this table shows exactly where the data went when it was split row by row. At the top, you see we're working with our iris split table that was created and off of our original iris data set that's provided by SAS. And on the left, SAS lists columns, and there's a new one called selected here. And um, I didn't mean to order that, so I'm going to redo it so you can see it where it was. If selected equals 1, that means that SAS put this row in our training set. And if SAS selected equals 0, that means that this row of data has been moved to our test data set. And this is how the procedure survey select keeps everything in one table while still making the split on our data. So if we look at just any of these rows where it is 1, um, That's a part of our data where the model used to find neighbors. And if we're looking at zero, that's what we were used to evaluate the performance of our model, meaning the model had to predict the species using the training rows. And the next we standardized. We standardized the values that are in the sepal length, the sepal width, the petal length, and the petal width column. So this table is a bridge between the raw data and the modeling step and shows which rows are training examples and which rows were held for testing and the exact predictors that we were about to scale and use for our neighbor distances. So this is an example of the code that you can use on any data set that you have. Um, and this is the process. You split your data into your training data and your testing data, and then you standardize your data. Don't forget that step. And then you run your classification. And you can do this on your data set. The same process applies. And that's pretty much everything for kNN. If you have any questions, feel free to email me. Um, Thank you for your time today. And I will see you later for more on data analytics. Bye.